It's my pleasure to introduce Mihnea Popa from Northwestern and to talk about Hodge theory.
Something. All right. Well, thanks for the invitation to speak. I'm having a great semester here so far. It's a pleasure to speak with so many friends. So what I will talk about is the following phenomenon: that projective manifolds usually cannot organize themselves arbitrarily in families that are again parametrized by projective manifolds. More precisely, if there is a lot of variation in the complex structure of the members of the family, or in the isomorphism class of the members of the family, that imposes very strong restrictions on what kind of parameter space there can be for that. Okay, and this is due to very subtle positivity phenomena on one hand in birational geometry and on the other hand in Hodge theory. Okay. So I want to start with some examples. In fact, the first real example is already the difficult theorem. But let me start with sort of a pre-example. It's not directly related to what I want to discuss, but at least it will show what sort of phenomena we will eventually encounter. So I'm just going to look at a map between two compact Riemann surfaces. Okay, so let's say, let's say that f from C1 to C2 is a holomorphic map, and C1 and C2 are compact Riemann surfaces, and the genus of C1 is G1, the genus of C2 is G2. Okay, so it's a fact about mappings, such mappings, that if the genus G1 is at least 2, okay, but G2 is equal to either 0, so this would mean we're looking at a P1, or if you want a Riemann sphere, or if the genus G2 is equal to 1, which means that we're looking at what we call an elliptic curve, okay, and the map is non-constant, then this mapping must necessarily be ramified. Okay, so maybe to adopt sort of complex geometry language, it's not submersive, or it's not a covering space. I mean, the sheets of this mapping have to come together somewhere. Okay, if the base is of one of these two types. And this is, one way to see this, for instance, is that there's a classical Riemann-Hurwitz formula. Which compares the two genera exactly in terms of where the map degenerates, namely twice the genus 1 minus the degree of the mapping minus twice 2 minus 1 is equal to the degree of the, this is the ramification locus. I won't get into too many details here, but I mean, this is precisely the locus upstairs, where the map is not ready. Okay, so in this particular, for these numbers, you can check immediately that this has to be positive. Okay, so there's something special about mappings to such bases, but what I really want to look at is families of positive dimensional manifolds. Okay, so morphisms with the fibers are positive dimensional, and kind of the next case to be looking at is a morphism where the fibers are compact Riemann surfaces and the base is a compact Riemann surface as well. Okay, so let's now do the next example of this sort. So what I'm saying now is that I'm looking at a holomorphic mapping between a projective surface to a compact Riemann surface. Let's say a genus G here. And so now the typical fiber is a compact Riemann surface, and there can be two types, generally speaking, two main types of such families. If you vary the fibers over the base C, the complex structure might stay the same generically, and that's what we call an isotrivial family. The complex structure, or isomorphism class of the general fiber does not change. It's like a product, for instance. Or you can have the opposite behavior where the complex structure does change as you move in the base, and that's called a non-isotrivial family. Okay, so now what happens if we have mappings to C to, again, Riemann surfaces of genus 0 or of genus 1? Well, this is the subject of an important result that's part of a very impressive package of conjectures that was put forward by Shafarevich and was solved in this particular case in some partial cases by Parshin and in general by Arkelo. Okay, so let me say this is a theorem. It's surprisingly difficult. Using a level of difficulty not much easier than what's going to come up later on. So, conjecture of Shafarevich. Part of the conjecture of Shafarevich. So this theorem of Arkelo. Okay, and this says that if F is non-isotrivial, and the genus of the fibers, let's say a fiber F, typical fiber F, general fiber F, is at least 2, then if the base has genus 0, just as before, then the family, right, so if this base of the family has genus 0, then the family must have at least 3 singular fibers. Okay, so then there exists at least 3 singular fibers. And if the genus is equal to 1, then there exists at least 1 singular fiber. Okay? So for such a family, if we have this condition that there's variation in the isomorphism class, then again the mapping cannot be submersive, and there's even a better kind of estimate here of how much this fails in the P1 case. Okay? So for those of you who are familiar, this is just a small aside, and it has no relevance really for the talk, but for those who are familiar with this language, this has a very nice kind of interpretation or reformulation, I should say, in terms of the moduli space of curves of genus G, or rather, I should strictly speaking say the moduli stack. But anyway, let's say MG is the moduli space. Just a remark. These G Riemann surfaces. This theorem says that when G is equal to 2, is greater or equal to 2, MG is what's called algebraically hyperbolic. This is a notion, it's an algebraic notion that kind of mimics, famous notion in complex geometry, if you want. And here it simply means that there are no non-constant morphisms to this space from C star, which now we want to think of as kind of being P1 minus 2 points, if you want. Or from elliptic curves. Okay, so I won't continue discussing this notion, but I just want to say that sometimes this type of theorem is called the hyperbolicity theorem. Alright, so we'd like to understand the behavior of higher dimensional families, or rather I should say families where both the fibers are allowed to be higher dimensional and the base is allowed to be higher dimensional. Okay, we'd like to be able to formulate similar, well, conjectures, results, and so on. And for that purpose, this language in the Champardovich conjecture is not satisfactory. Right? So, in order to look at higher dimensional generalizations, our first task is to introduce or sort of rephrase this theorem in a completely different language that can be generalized to higher dimensional manifolds. Okay, so now I'm going to sort of backtrack a little bit and just introduce some basic invariants in complex geometry. Alright, so if we look at a complex manifold, okay, then I can consider its holomorphic tangent bundle, or its dual. Say this is the holomorphic cotangent bundle. This is the bundle of holomorphic 1 forms of X. For any non-negative integer, I can also consider the exterior powers of this cotangent bundle. So these are the bundles of holomorphic P forms of X. Okay, and of very special significance is the case when P is maximal, it's equal to n, which is the dimension of X over C. Okay, so in this case, we're looking at the top exterior power of the holomorphic cotangent bundle. This has, there's special notation and a special name for this. This is what's called a canonical bundle of X. Okay, kind of, arguably the most important holomorphic invariant of the manifold X. And because we're looking at the top exterior power, this is in fact a vector bundle of rank 1. This is what we usually call a line bundle in complex geometry. And it produces in particular a bunch of numerical invariants for us associated to the manifold X. Right? So I could, for instance, look at how many linear independent global sections this line bundle has, if it has any. And I can also look at holomorphic tensors associated with this line bundle and see how many global holomorphic sections those have. And so the notation will be this. Pm of X usually denotes the dimension over C of the space of global sections of the vector bundle actually continues to be a line bundle, omega X to any sort of tensor power n. So that, in this particular case, we're going to go to 0. Okay? It's well known that these spaces are finite dimensional over C. We're just counting their dimension. And there is a famous theorem called the Riemann theorem in algebraic geometry, which basically tells us that asymptotically, seen as a function of m, this has polynomial behavior. And so coarser invariant, these are called the Venturi genera. X. This is the mth Fourier genus of X, just to denote the fact that it sort of generalizes the notion of the genus of a Riemann surface. But in particular, these grow polynomially, and we can actually look at the degree of that polynomial. So this is a coarser invariant, like a Dirac dimension of X. And let me, if you don't mind, this is kind of bad, but let me just write it like this. It's basically defined by saying that Pm of X kind of grows like n to the power kappa of X. Okay. Alright? And the same Riemann theorem tells us that this can never exceed the dimension of X. Okay? But we take this as a definition that X is a manifold of general type if we have equality here. So if the Dirac dimension is equal to the dimension of X. Okay, so this might look kind of like a series of technical definitions if you haven't seen these notions before, so it's probably better to just try to understand them through a few examples. Okay, so I want to give a few examples of manifolds that are of general type, and then a few that are not, and what it really means to not be a general type. Okay, so let's go back to the case of Riemann surfaces. We're going to consider a compact Riemann surface of genus G. Okay, so if the genus is 0, as I said, this is the case of the projected line, then there are no forms whatsoever in omega x or in powers of omega x. These plurigenera are always equal to 0, and so we just take it as a definition. It's just a convention. We say that in this case, the dimension is equal to minus infinity. If the genus is 1, we're looking at an elliptic curve, so this is a torus. The canonical bundle is trivial, all of its powers are trivial, there's always just one section, right? So the plurigenera are always equal to 1 for elliptic curves, and therefore the growth is, it's a zero-dimensional, zero-degree polynomial, but the higher dimension is equal to 0. But if the genus is at least 2, then these plurigenera can actually be computed from the Riemann-Roch formula for curves, and for m sufficiently large, they look something like this if I didn't make a mistake, but in any case, they have linear growth, and so the higher dimension is equal to 1. And so this is our definition of a manifold of general type. Okay, so in this case, general type is equivalent to having genus at least 2 for compact Riemann surfaces. Okay, there are other basic examples of such manifolds. For instance, you could be looking at the hypersurface in projective space. Okay, so let's say this is the zero locus of a polynomial of degree d, a homogeneous polynomial of degree d. And it turns out that these are of general type, if and only if d is sufficiently large, in fact, at least n plus 2. Okay, so x is of general type. It's at least n plus 2. Okay. Another kind of ubiquitous type of example is to look at submanifolds of tori. So it turns out that most projective submanifolds,
if n is the dimension of the projective space, it's at n plus 3 rather than n plus 2. So for example,
if n plus 1, it's a lot.
Oh, I'm sorry, it's the dimension of the
canonical bundle of
the canonical bundle of projective space. Yeah.
So, if I look at projective submanifolds of tori, most of them are of general type. In fact, to not be of general type means to be fibered in subtori of that torus. Kind of like a very special condition, right? So here we see another interesting class of examples. All of these examples actually are special cases of a very general class that's kind of very important and at the same time special inside the world of what is of general type. So that's manifolds with negative first terms. Okay? So sometimes we say that omega x is positive in differential geometric language. This means it has a metric whose curvature is positive. Or we say ample in algebraic geometric language, equivalent notions. Or if you want in even more differential geometric terms, this is equivalent by kind of a famous theorem of Yao, with the fact that the tangent bundle has a metric with constant negative feature curvature. Okay, so all of the notions that I explained up to now fit in this category, but there are, of course, many other examples that don't, and the main reason for this is the fact that if you look at these invariants that I defined here, one can see that they don't change under bimeromorphic equivalence. Okay, so I could consider birational or bimeromorphic models of the varieties that I'm looking at, and these invariants are the same. So, while I preserve the condition of being of general type, this step of strong positivity condition disappears. Right? So let me just say for now, bimeromorphic models of such. Again, if you're familiar with moduli spaces, here I'm checking a little bit because one could allow singularities, but many examples of moduli spaces are of this sort, and so on. Okay, but what is not a general type? Okay, so you could be looking at something like Pn, projective space where there are no forms whatsoever, or, more generally, X with the opposite condition of what I considered there, whose Chern class is strictly positive. These are Fano manifolds. Okay, so these are, if you look at by analogy with the case of curve, these would be manifolds whose Kodara dimension is minus infinity. They know forms. Or you could be looking, for instance, at Calabi-Yau manifolds. Okay, so sorry, I should say, these are not of general type. You could be looking at Calabi-Yau manifolds, where in some sense or another, we want to say, just very loosely speaking, that the canonical bundle is trivial, like K3 surfaces, like tori, etc., elliptic vibrations over such things and so on. These are manifolds where, by analogy to this case, they would have Kodara dimension 0. In general, more things can happen, but the rough idea, the rough picture to keep in mind is that something that's not of general type will at least, bimeromorphically be fibered in such examples over a lower dimensional map. That's kind of the story. Okay, so these are some examples. Let's actually go back one more time to the case of compact Riemann surfaces. Okay, so we've seen that for a compact Riemann surface of genus G, general type was equivalent to saying that the genus is at least 2, and that just, hopefully you agree with this, that's also equivalent to saying that 2G minus 2 is strictly bigger than 0. Okay, so this happens to be, in the case of Riemann surfaces, precisely this minus C1 of C that I was talking about earlier, or, what we usually call the degree of the canonical bundle of this Riemann surface. So I want to interpret the notion of being of general type in terms of this degree right now. And so you saw that this is not positive precisely when we're looking at genus 0 or genus 1. And so now we're just going to do kind of apparently silly thing, right? Just going to force it to be positive by adding a few points. Okay, so instead of this, I could just consider delta in set C to be a finite set of points. Okay, so I could look at the degree of a formal symbol here, omega C of delta. So you could just take it as a formal symbol, and I'll just tell you that by definition the degree of this thing is 2G minus 2 plus the number of points of delta. Or, it is actually true that this makes sense as another line bundle, vector bundle of rank 1 on the Riemann surface. You could make sense of this notion, and it really would be the first Chern class of that line bundle. Okay, so that's the degree of that line bundle, and now you see that this is strictly positive when the genus is equal to 0, and the number of points in delta is at least 3, and it's strictly positive when the genus is equal to 1, and the number of points in delta is at least 1. That's exactly what appeared in the conclusion of Shafarevitch's, or, the Archilov partial theorem. Okay, and, we want to give a name to such things. If I have a pair with this, with these properties, I just call this a log general. Okay? there's no problem to make sense of this notion in arbitrary dimension. Alright, so we could, this makes sense when y is n manifold. Now instead of delta, instead of finite set of points, I have to consider in y what's usually called a divisor. By this I mean just, let's say, roughly speaking, the union of codimension 1 sub varieties, analytic subspaces if you want. And again, one can make sense of this line bundle. Sorry, let me put it here. It's not so important getting into the technical details of this, but we can again make sense of this line bundle omega y of delta. We can look at the growth of the space of sections for all the tensor powers of this line bundle, right? So the sections, dimension of the sections of omega y of delta to the power m. Okay, and if this grows again like m to the dimension of x, we say that the pair yd is of log general type. Okay, so yet again a technical definition that perhaps doesn't make so much sense, and let's again look at a few examples just to get an idea what type of pairs we're looking at. So let's look at Pn, for instance, the higher dimensional analog of the projective line. Before I had 3 points, well, in general, one natural thing to consider here is just the union of hyperplanes. Okay, so for instance, I could take D to be just a bunch of hyperplanes in Pn, and so it turns out that this pair is of log general type. If and only if the number r is at least n plus 2 again. Okay? So you could never, this was 3 before, but in general you cannot support such a pair like pure this many hyperplanes. Okay? And if you're looking at, maybe I should switch to this language if you don't mind. It's not actually really necessary for most of the results, but if you look at an abelian variety, and by this I mean simply a complex torus that happens to be projected. Okay, so if you look at an abelian variety, in fact, any divisor will do, as long as it's non-empty. So here I can take anything which is non-empty. It's very nice. This can automatically becomes a log general type.
Or for any projected y, there always is such a d, but the game is to try to make it not a very large divisior, right? As long as you take the extremely...
Right, that's right, exactly. Yeah. And then, if you look at Calabi-Yao's, here, if x is Calabi-Yao, then maybe it's a little bit harder to actually say precisely, in easier terms, but, you can take D to be, let's say, a suitably positive divisor. So I can't really get into this, but it's what algebraic geometers call a big divisor. So again, once we're given such a thing, then the pair becomes a log general. Alright, so we're almost set, right? So in Shaparevich's conjecture, we had families of compact Riemann surfaces of general type, and the base of the family turned out to be a pair of log general type. But we still have a problem. Okay, to generalize to higher dimension, the problem is the notion of being isotrivial. Okay, so over a Riemann surface you don't have space, right? Either you're isotrivial or you're non-isotrivial. But if you look in higher dimension, you can have families which are isotrivial in one direction and non-isotrivial in another direction, right? So there's kind of a mixed behavior that you have to take into account. There's also a problem with the fibers.
So for isotrivial, is there some binary-morphic version of that?
Yeah, it's coming in a second. You're absolutely right. Yeah, so, okay, but there, speaking of bimeromorphic, this is an issue with the fibers, right? So we have fibers that are come by Riemann surfaces. So there we didn't see this phenomenon of birational modifications. But what we should really be looking at is the equivalence of the fibers up to birational equivalence, or bimeromorphic equivalence, right? As I said, you can just perform some small surgery on your manifold and have it stay in the same birational equivalence class. And so both of these problems were solved at the same time by a definition due to Fiebig. Well, I won't say definition. He introduced what's called the variation of a family. Okay, the variation of a family, holomorphism. So I should emphasize there are many, many brilliant solutions to the problems that appear in the subjects, and they are Fiebigs. You know, most of them are due to Fiebig. I mean, he really kind of always taught us how to proceed in questions of this sort. Variation of a family is it's very technical to define precisely, and I won't attempt to do so, but I can give you some intuition. First of all, I should just say that I mean, you can imagine what it means given what I said earlier about various directions. I mean, this is really the number of parameters or moduli, if you want, for the bimeromorphic equivalence classes of fibers. So like I said, this can be made precise with algebraic language, but yet again, for those who are familiar with the notion of moduli spaces, if you had a moduli space parametrizing objects like the fibers of this morphism, and the family were obtained by mapping Y into that moduli space, then the variation would be precisely the image of that the dimension of the image of that moduli map. Okay? But, of course, we don't have something like this at our disposal in general, but I can make perfect sense of what it means to have minimal variation or maximal variation. Okay, so first this answers Jason's question. So you could look at variation, the variation is equal to 0. Okay, so this would be minimal. This is what Fiebig calls birationally isotrivial. Okay, and this simply means precisely on an open, dense subset in Y, all fibers are birational to each other. Okay, so this is sort of the analog of our old notion of isotriviality, right? So this would be kind of represent the old isotrivial from now on. And I can also make sense precisely of what it means to have variation equal to the dimension of Y. This is the maximum allowed, and therefore it's called maximal variation. Okay, and this means that the general fiber is bimeromorphic to at most countably many other fibers. I'm sorry for this here. To at most countably many others. So in other words, you're not allowed to be birationally isotrivial along any one parameter direction. Okay, so these are the main types of variation of family that we'll be concerned with. Okay, so now with this language, we're actually able to formulate some generalizations of Schaffarich's conjecture. But before I make any concrete statements, I should say, that this is kind of just to remember for the rest of the talk, so I don't say this too many times that every time it comes up. When F is a family such that the general fiber has ample canonical bundle, positive canonical bundle. Okay, so this was this special class of, the very important class of varieties of general type have strictly negative first term class, then all of the results that I'll discuss below are already known. And this is due to work of many, many people over many, many years, and it starts again with really important work of Fleabag and Zuo. Allow me to just say sort of the most important names here without getting into too many details. There is work of Quebec's Hodge on this, and there's some work of Colloquium. There is work of G, who gave us a nice lecture yesterday. There is work of Campana and Brook that finally sort of kind of, let's say, kind of wrapped up all these, or most of the issues that surround the families of what's called canonically polarized manifolds. Okay, everything that is new in what I'm going to say later on. Or almost everything that is new, and one small exception, so let's say everything new is going to the colleague, Christian Schnell. So, Christian Schnell, you can read. And so if you don't like the results, take it out of here. Okay. So, alright. So, what do we want to do? Well, if you go back to this theorem of Arkelov and Parshin, we could actually imagine different ways of generalizing. So, for instance, there was, part of it was a statement about not having submersive varying families over an elliptic curve. So we could think of generalizing this to families parametrized by higher dimensional tori. Or we could just take the full package and understand what it means to have a family with maximal variation, what kind of restrictions that imposes on the base. Okay, so let me make this precise. Okay, so the first type of generalization is to families over, let me again I'll think of projective tori, like I said. This could be done even more generally, but let's say over 1 billion varieties. That is projected. Okay, so I'll start with the corollary. Okay, this is not the main result, but it's the result that's phrased in the language that I discussed up to now. Okay, so this corollary says that if I have a submersive map, so what, submersive, or, we call this a smooth morphism in algebraic geometry, from a projective manifold to an abelian variety. Okay, so this is just some projective manifold. This is an abelian variety, but whose fibers are of general type. These are arbitrary manifolds of general type. Then F has to be birationally executed. Okay, so this is that zero variation that I was referencing earlier. Okay. So again, just compare, it takes a while to kind of make this translation back and forth. That piece of the Arkelov-Parshin theorem says if you have a non-isotrivial family of compact Riemann surfaces of genus at least 2 over an elliptic curve, then that cannot be submersive. So that fully extends to arbitrary dimension, right? But in this kind of birational equivalent set, right? This is the one way to extend that. Okay. So, why is this true? Or at least, some kind of logical implications that lead to that.
Is there some simple example which shows that it has to be, can only be birational isotrivial, or are there examples where it's not isotrivial, but it's...
Well, I mean, the thing is that I can always blow up. I mean, because I'm not imposing any strict positivity conditions.
Yes, but
yeah, that's exactly.
If you had a section, you could blow along with.
Yeah, that's right. Yeah.
But then,
so I can easily. So the problem is, if you want to go backwards, then you have to introduce singular fibers.
So I was just thinking that when since you assume it's submersive, you can't just blow up some particular fiber.
Yeah, that's right. But you could blow up some, like you said. Yeah, exactly. Yeah, that's right. So you have to be very careful, but it's possible.
That's
right. And in fact, yeah, so, okay, anyway. Alright, so the theorem that implies this is a theorem that's maybe we proved a few years ago, and this answers a conjecture of Aiken and Hodge. I mentioned earlier that they had some results in the canonically polarized case, and also of Lu and Zhang. Okay, and this says that, I mean, it's kind of like its more basic form that doesn't quite apply here. It says that if X is of general type, then every holomorphic one form on X vanishes at some point. Okay, so it's kind of a basic statement that seems a little bit unrelated to the problem that we're discussing here. And in fact, it's not quite sufficient to prove this. But what we need to do is to extend the statement to arbitrary manifolds that are not necessarily of general type. Okay, and this will not be true anymore, of course, but it's possible to say something. So more generally, if X is arbitrary, but W is a linear subspace in the space of holomorphic one forms on X, such that every non-zero element in W is a nowhere vanishing form. Then W cannot be arbitrarily large. In fact, the dimension of this space has to be bounded by this birational invariant, the dimension of X minus the quadratic dimension of X. Okay? So, this case here is just a case when the two numbers are the same. Okay, that's kind of when this gadget is equal to 0, but in general, there is still this behavior where you can say something interesting, or you cannot have such large spaces of nowhere vanishing one forms on your manifold. And this actually leads to results about families of varieties. Because you see there's kind of an immediate corollary of this that we can deduce about maps to tori. Okay, so let's say corollary prime says that if F from X to A is a submersive map to an abelian variety, then the dimension of A has to be bounded by the dimension of X minus the quadratic dimension of X. Okay, this is the type of statement that we're aiming for, that you cannot have kind of arbitrary maps, submersive maps on a abelian variety. There's an upper bound on how large this abelian variety can be. Again, in terms of this birational invariant. Okay, so how do you prove this? You just take W to be the pullback of the space of holomorphic one forms on A. On a torus, all non-trivial one forms are nowhere vanishing. You pull it back to here, and then it falls exactly in this category. Okay? And so this tells, okay, so I mean, I should say, even the case when X is of general type is interesting. This was kind of a Folkville conjecture, or maybe a conjecture of feedback, I'm not completely sure. Which said, but the case when X is of general type says that there cannot be submersive maps from a manifold of general type to an abelian variety. Alright, so from corollary prime to the corollary, maybe I won't insist so much, but this you have to use a theorem of Kolar. Corollary prime plus the theorem of Kolar is a bit technical to get into. So this is the solution to the Itaka-Fita CNN conjecture for families with fibers of general type. That's another numerical condition that's imposed by this family. Here's one numerical condition. If you put those two together, you get precisely that the variation is equal to 0. Okay, so that's okay. So that's the story when you have mappings to Torah. And now perhaps sort of the more encompassing generalization is this story about families with maximal variation. Okay, so here's a fundamental conjecture that was proposed by Philae, that sort of a vast generalization of Shafarevич's conjecture. Okay, so he proposed the following. If we have a family, so a surjective morphism, surjective manifolds, with maximal variation, right? So recall, this is our new notion of being non-isotrivial, so like in the strongest possible sense. And such that, and we denote, and we assume that the singular locus of F is contained in some divisor D. Okay, so Codimension 1 subspace. Okay, so here I could easily put equal because I can realize that by rational multiplication. So let's just take it. I mean, let's say that any divisor D that contains the singular locus, so like the locus where the map is not submersive. Okay. And we assume that the fibers have positive canonical bundle. So this kind of like strong general type condition, like the case of compact Riemann surfaces of genus at least 2. Then the conjecture states that the pair YD is of log general type. So that's exactly what we saw earlier in Shafarevич's, in the Arkelov-Farsian theorem, right? So the condition there, the conclusion there, was that if we have such a family of Riemann surfaces over a Riemann surface, then we get P1 and these 3 points, or we get a liquid curve of at least 1 length. Right? So it's kind of that's the version of this. Okay, and as I said, because this is a conjecture about fibers that are canonically polarized, this is already known. So this was the work of Kovac and Patakov, and especially, kind of fully wrapped up by Kampanak known piece. Okay. Alright, so what we sort of proposed last year is that the hypothesis in this conjecture is still too strong. In fact, it's not necessary to impose positivity on the fibers. We can relax this to arbitrary families of varieties of general type, but in fact, at least, conjecturally for now, this should be relaxed to arbitrary families of varieties, the maximal variation. So let me be precise. Okay, so the theorem that Christian and I proved is that Philae's conjecture holds whenever F, the fiber of the family, is of general type, or even, I'll explain this, let me just say it and I'll say it a couple of words later, when it has what's called a good minimal model. Okay, so this is again one of those technical definitions that appear in birational geometry. The few words that I want to say about this, that one of the most important, maybe the most important theorem that was proved in birational geometry and algebraic geometry in recent years says that a variety of general type has a good minimal model. But the most important conjecture that's open in birational geometry says that essentially any variety has a good model. In fact, at least any variety with non-negative quadratic dimension. So conjecturally, any variety, family of varieties with quadratic dimension. Okay, this is called the abundance conjecture. It's kind of the goal of the minimal model. Okay, but of course, sometimes we already have families that are presented as such. Like this applies already to families of Calabi-Yaos, families that are already themselves smooth minimal models. Just so you understand. Okay? So, this is the story in the sense of variation. In fact, what really matters is just the variation. Okay, so I guess now it's time to say a few words about how one approaches results of this sort. Okay, so some ideas about how to attack such results. And, okay, so I should say, let me just kind of offer first sort of a slogan, right? So the approach is the sort of the keeping track of positivity. Game. Okay. So there's sort of a keeping track of positivity game here. And the idea is that there are different kinds of positivity that appear in this problem. There's positivity that's associated to natural Hodge theoretic objects that come into play whenever one looks at a family of manifolds. And there is, so that's already there. And then there's positivity that comes from this hypothesis of having maximal variation. It's positivity from birational geometry. And the point is that these kind of clash with each other. Okay, so they produce some subtle positivity related to holomorphic tensors, tensor powers of cotangent bundle, but in kind of a subtle way. And from there, one needs to eventually get to these twisted cotangent bundles that appear in the conclusion. Okay, so a bit more precisely, let's look first at the sort of the best case scenario, where F is already a smooth family. Okay, so here, so we're looking at let's write it like this, as a family, we're looking at a morphism like this. So for every point in Y, I can look at the singular cohomology of the fiber over that point. Right? So the
smooth family just mean all the fibers are smooth?
Yeah, that's right. Yeah, all the fibers are smooth. Yeah. So I can look at the singular cohomology of the fiber.
So you're assuming that F is a smooth submersion?
Yeah, exactly. Smooth submersion.
So in particular, the fibers are all.
Yeah, that's right. In particular, the fibers are also. Okay, so I look at the singular cohomology of the fibers, and this is a topological invariant, but then on this, because it's a family of projected manifolds, particularly Kähler manifolds, it also comes with a Hodge filtration. So let's just say that K is the dimension of the fibers here, just to take one particular case. Okay, there's a filtration by linear subspaces that goes all the way down to Fk, Ha, and now these spaces have holomorphic interpretation. They can be interpreted in terms of bundles of holomorphic forms on the fibers, and in particular, this guy here is just the sections. The space of global sections of the canonical bundle of the respective fiber. Okay? So now, as Griffiths taught us, what we should do is to start varying Y and Y. Okay? And as we vary Y and Y, First, the spaces, the singular cohomology spaces organize themselves into what's called a local system, a complex local system. These form a complex local system, or if you want, equivalently, if we tensor with the functions on the base, these give us a vector bundle, complex vector bundle with a flat connection. Okay, and also these spaces in the filtration, they vary holomorphically over the base, and they organize themselves into subbundles of E. Okay, this is part of the data of what's called the variation of Hodge structure, and Griffiths proved some results about such bundles that hold for any variation, polarized variation of Hodge structure. He showed, for instance, let's take E to be this lowest one. I said the fiber by fiber is the global section, so this is what algebraic, it's a very important object for algebraic geometers. This is what's usually called the push forward of the relative canonical bundle of the family. And Griffiths showed, among other things, that E has it's called a Hodge metric. Anyways, it has a metric with non-negative curvature. Okay, so some positivity is already there. But even better, if this Hodge structure, fiber by fiber, this data that I presented here, fiber by fiber varies maximally in this family, so that the Hodge structure varies maximally, which is less than what we want, by the way. We want the variation of the actual manifolds. But in any case, then there exists some point where the curvature is strictly positive. Okay.
What does maximal variation mean here?
There's, let's say the map to the period domain is kind of locally injected.
What does all of this mean?
Sense of Hodge structure. But it's not what we want. This is not the way to go because it doesn't solve our problem.
I have a question. Yeah, what if you're talking about families of Godot surfaces or something like that where E is 0? Just because omega is ample doesn't mean it has any global sections.
Just because omega is. I'm not sure how to. So, perhaps there is no. I cannot have maximal variation for the Hodge structure. I don't know. I have to think about it. Okay, sorry, I cannot answer it.
It's really into that.
Plus, I'm messing up with my timing here too. Okay, so let me say very briefly. Okay, so in the general case,
nonsense, so it's fine.
In the general case, okay, so there will be this singular locus of the mapping. Okay, so we have the same picture over the components of the singular locus in the base. Okay, so we can still consider this variation of the Hodge structure over this locus, but we'd really like to extend this object to the whole compact Y and work with its projected variety. So this data, this variation of Hodge structure that I was talking about earlier, extends to what's called a Hodge moduli over Y. So this is kind of the main object that we introduced in this study and we used to sort of extend these results. And this Hodge module, in particular, the vector bundle with flat connection extends to what's called a D module, a dy module, together with a good filtration in the sense of D modules. Okay, so M is an object. Now it's just a sheaf, it's not a vector bundle, but again it has a connection-like operation. Again, it has a connection-like operation as before, so it extends the notion of bundle with flat connection, but it's not required to be a vector bundle anymore. It could be pretty nasty at the boundary points. There is a filtration, just very briefly, I'll say this in a minute. There is a filtration, an increasing filtration, that is still called the Hodge filtration, that extends this Hodge filtration over this smooth locus. This filtration has nice properties. The kth piece is mapped to, by the connection, to the k plus first piece times omega 1. Okay, so, in the world of variation of Hodge structures, this is a property that's called Bridges transversality, or D module, and it has to be basically part of the definition of being a filtration in the sense of D modules. One can pass to the associated graded quotients for this filtration, and there's still a reduced mapping like that. And now these again are algebrogeometric objects. These turn out, this is what's called sometimes a generalized Kodara-Spencer morphism. They are linear over the holomorphic function in the base. They're all isomorphism. And as opposed to the best case scenario, these could be very nasty objects somehow. They are vector bundles over the open set, but they could actually have torsion. They can go much further than that K where the Hodge filtration stops because of the singularities and so on. I mean, they're really complicated. But the lowest one, just as before, the lowest one is still equal to the push forward of the relative canonical bundle. That's the one calculation that can be done, and this is great. And then they also retain a shadow of positivity. Okay, so there's a theorem that I proved together with Leibou just last year, that the kernels of all these morphisms, of all of them, are what's called weakly negative. Whatever, this is a notion again introduced by Fiebig, again in variational geometry, again pretty complicated, but in any case, there is still some shadow of positivity, or rather negativity, that survives even in this kind of generalized variation of Hodge structure picture. So the birational variation of the family tells us, because of very important theorem of Kolar, Kawamata, and Fiebig, that this object here contains positive subobjects. This is where birational geometry comes into play. While this sort of generalized Hodge theory picture introduces some negativity into the picture. They clash with each other, they produce positivity inside powers of the cotangent bundle, and then because of an important theorem of Campana and all, this leads to the notion of log general case. And I'm sorry, but I went over. Thank you.
Questions, comments?
Yes.
So over here, in this Griffiths construction, I'm not sure what the Hodge metric is, but I know another metric for this bundle.
Hodge metric is given by the polarization of fibers.
Okay, so this metric is just, it actually works really well in the birational category. Because you have these very canonical sections, you can just take their L2 norm. And it's well defined outside of subvarieties. This is this variance of this metric.
Yes. Okay.
And
yeah, that's right.
One of these theorems is that this also has non-negative curvatures. But the nice thing is that it works even when you have lots of singularities.
But still in this kind of weak positivity sense, right? But it's kind of a singular metric.
It's a singular metric.
Yeah. So this would be the analog of something like this in algebraic geometry. That's exactly that, right? I mean, rather the dual of these kernels, which is what we use, I mean, that extends the Griffith's picture of the non-negative metric, the dual of these Kodara-Spencer. Okay, and for instance, that theorem fits here. So that's the kind of the analytic analog of weak positivity. Now that holds in much bigger generality where you have powers of relative canonical bundles, and that also comes into play here. And I don't know.
So you also have like a relative, right? The thing about variances stuff is that it also works in the log category.
Right, so, yeah, so Christian and I have a theorem, but that goes in a different direction. Christian and I have a theorem that is pushed forward where canonical bundles are positive and sort of this, the algebra geometry version of that. But that's a really big difference.
And then over here about this what I really wanted to ask about this weakly negative thing is, I mean, the way that this theorem is proved in the Berenson's metric is actually like, it's essentially a vanishing theorem, but it's with estimates. So it comes from Riemann. So it's like a vanishing theorem, but it works for very singular metrics as well. So how do you get this negativity?
Okay, so this
is there a simple answer?
Yes, there is a simple answer, but it's not that way. Okay. So it's by successive, reduction after reduction after reduction, using Saito's deepest results in his theory to the case of the canonical extensions, where people like, Zuo and Brunebart and so on, they generalize this statement here. So finally, this reduces to a metric statement. I am really hoping for a proof using vanishing theorems, but I don't know how to do it yet. However, I can prove, anyway, sorry.
I imagine that Mihnea tried to prove that very statement for this.
Maybe not for these objects. Right. Only for powers of pluricanonical bundles. They don't fit here. They don't fit in here. Those are not Hodge theory. So there's a slight difference. These two worlds overlap only on that guy over there. Okay. Yeah. Okay. Let's try that.